Good afternoon, everybody. So we have a seminar this afternoon from Igor Podlubny from the Technical University of Kosice. He's going to talk to us on the evolution of generalized differentiation.
Okay, so thank you very much for coming here. I will start with those expressions of gratitude to the Institute that provides a wonderful environment for doing research, and to the organizers that also allowed me to take part in this wonderful program. And my special thanks are also to Adrian Rice, one of the organizers, who even put me in the same room with Jesper Lutzen, and it had some real meaning. I like that. So the topic of my talk is related to my research. My research is actually in the field of fractional order derivatives, fractional order differential equations, fractional order modeling, applications in control and engineering and natural sciences. And of course, doing such kind of research, I am interested in the way of thinking of the predecessors of the people who created the field, who contributed to this field. And so this is why I am here, and I would like to share some basic information about that with you. First, I'm coming from Slovakia. You see it is surrounded by Ukraine, Poland, Hungary, Austria, and Czech Republic. And my hometown is Kosice, and if you never heard about this, I can tell you that it is the place of the third oldest city marathon. I mean modern marathons, not those ancient Greece. So Boston was the first, Yonkers the second, and Kosice since 1924. But let me go straight to the topic. So the idea is more or less trivial: transition from integer to non-integer. And this idea is omnipresent. For example, I can recall the notion of numbers. It took several thousand years to come from counting, from natural numbers, to the notion introduced by Dedekind in the mid-19th century. The same story was with repeated multiplication, for example. X to power n is repeated multiplication, and in this way directly it cannot be generalized, but with appearance of the exponential function and the logarithmic function, it was possible to write that repeated differentiation in the way that allows n to be non-integer. So we can evaluate the expression on the right for any n and attribute this value to what we see on the left. Basic idea of regularization. With the factorial, the story is the same. The gamma function allows to generalize this notion to non-integer values of the argument. And of course, even notation then changes, it is clear. We are basically surrounded by this idea from integer to non-integer. A set of wrenches sometimes is replaced just by an adjustable wrench. Convenient. You don't need to have all possible sizes. People here use bikes a lot, so those gears in the bike, they are discrete, as you see here, or manual gears in the cars. Now they are basically replaced by something like CVTs or other continuous kinds of continuous gear. So from integer to non-integer, the idea is omnipresent. And so the general picture could be like this. So we have a sequence of repeated differentiations of order 1, 2, 3, and so forth, and repeated integrations in some sense. And we have that general understanding that differentiation and integration are somehow mutually inverse. So let us denote integrations by negative indices, and then we have actually something that we have already seen on the real line, the sequence of integers. And so the question is how to interpolate between those operations in this case. Not between the values, but between the operators. How to generalize this? And which properties should be preserved? If we generalize to non-integer values of orders. Of course, we have zeroth derivative to be equal to the function. We have to preserve the index law, and we have to preserve linearity. This is if we would look at the problem now. But the historical development is different. We look only forward, and not always we have this possibility to look back and say, okay, this is the way how we should look at that. I like very much the paper by Judith Grabiner, published in 1983, and in Mathematics magazine, about the development of the idea of differentiation. And she came with a wonderful statement. And I would apply this statement to any notion that we have in mathematics. First used, then discovered, then explored and developed, and only after that defined. And we can project this statement onto different notions in mathematics, and basically I think we might all agree with that. So what happened with the notion of generalized differentiation? The differentiation, well, was introduced by Newton and Leibniz. And what happens here is, from the very beginning, Newton was using dots for denoting derivatives. Lagrange also used primes, right? But it was exactly that counting, 1 or 2 or 3. And it was like playing on an ancient harp, where each string produces only one sound. Leibniz came with another notation. Basically, he was using this one, like for differentials, but in the sense of derivatives. I will also use this modern notation freely. So he introduced the symbol here. And good notation is a wonderful tool, because good notation is provocative. It provokes thinking. And so L'Hopital had the reason to ask Leibniz, what if the order n will be, say, 1/2 or something else? And Leibniz replied that, okay, I cannot explain this right now, but useful consequences will be drawn. We know this from the publications of the correspondence between Leibniz and other people like L'Hopital. And the first collection of such correspondence was published in 1849. And in the letter dated September 30, 1695, Leibniz replied what we see here. It looks like one day we will, this is the exact quotation, one day we will draw very useful consequences from these paradoxes, because there are hardly any paradoxes without utility. Not so long time ago, about 20 years ago, there was the second edition, another edition of the correspondence. And I like this very much, because the correspondence was handwritten, it wasn't an email. And so in the new edition, some new things were actually added from that correspondence that were omitted in the 19th century. So this is the publication in Germany, Academia Verlag, 2004. Basically the same thing, but what we see here, I like very much. Leibniz provides the following examples and continues. If we replace x with dx, this actually changes to negative quantities and converts derivative into integral. It is 1695, okay? Very interesting story, and it's not all. So he started looking at this himself, and noticed that differentiation of the exponential function is very convenient, and the expression on the right here allows to attribute the meaning to something on the left. So basically, derivative of order n of the exponential function can be defined using this expression. Very interesting and not bad, because that was really the very first step. The idea was born, and it had to wait until Euler and his famous paper in the St. Petersburg proceedings of the Academia Petropolitana. And 1738 paper, this is something unbelievable. He introduces here the beta function first, the gamma function after that. This is what we call now beta and gamma. He did not give them the names. And then he uses the gamma function immediately for differentiation of the power function, not the exponential, but the power function. And even more, I will show you in a moment. So basically, this is very straightforward drive by Euler. And you see here, he introduces, he has those tools, and he goes to evaluate the derivative of the power function. The expression that he obtains is here, and this ratio of the two integrals is the ratio of the two gamma functions. He was using logarithmic version of the definition of the gamma function. You see here, letter L stands for the logarithm. And then the result is here. As particular case, half-order derivative of z is equal to the following expression. This is absolutely correct even today. So I like this paper very much. And for example, I like it also because of the order of appearance. If I go now to the textbook on special functions, I see first gamma function, then beta function. But Euler did it in the way I told you. First beta, then gamma. And I like also that immediate application to differentiation. The idea was in the air. So this is his result. And when I was reading this paper, I got an impression that it is unfinished. With his tools, he could evaluate also integrals of arbitrary order, not only derivatives of the power function. So I wrote 3 extra paragraphs to Euler's paper, imitating his Latin and his typeset and old fonts. Yeah. And here I demonstrate that he could evaluate the fractional order integrals of the power function, and to demonstrate that fractional order integration and differentiation are mutually inverse. Okay. There is more in this paper, because if we look at the paper closely, we see that there is also a differential equation. For the first time ever, fractional order differential equation appears here. The problem is formal, geometric one. He had to do something with this, and he was curious and very inventive, and he obtains the solution. So this is just a beautiful paper. 4 such results. This is the paper I really like, not those papers that now people produce in high quantities without real contributions. One monumental paper with monumental results. And it was so nicely presented that Lacroix included it in the textbook. So we don't have fractional order modeling and derivatives in the textbooks now, but Lacroix already did this in volume 3 of his textbook of differential and integral calculus in 1819. And he actually reproduces what Euler did, and we see here the final result in the same form as Euler obtained. But here there is that ratio of the 2 integrals that we call now gammas. And basically this asks for good notation. At this point, the notation is required. And okay, the notation comes on request. And Adrien-Marie Legendre, you know the story of this picture. Initially, it was believed that the picture you see now is the portrait of Legendre. It was not. The full story was published in Notices of American Mathematical Society in 2009. And the only picture we have now is this one. This is Legendre. A grotesque from the meeting of the Paris Academy. And the other person here is Fourier. Yeah?
You have the name.
On the left is Legendre, on the right is Fourier. Okay, so, and Legendre was the person who introduced the notation for what we call the gamma function. By the way, who introduced the notation for the beta function? It was Joseph Binet. I looked at those names and I thought to myself, okay, something is strange here. I see here something reminded me Legendre initial and something Binet initial. Yeah? Those are just flipped upside down. What was the reason? I don't know, but this is a strange observation. And if I look at how Legendre introduced the function, I see another nice detail. The equations were numbered using Greek letters, alpha, beta, and so forth. And this relationship, introducing the symbol that we call now the gamma function, is numbered gamma. I like this. By the way, later it became obvious that there is also the need for some generalized exponential. Much later, it was already in 20th century. And who came with the generalized exponential for us, for fractional order people? It is Gustav Magnusson Metagler. And he was not like Legendre or Binet. He just used the capital E as for exponential. Generalized exponential with the index alpha for his purposes in his field of complex analysis. And later it became obvious that we need actually such generalized exponential with 2 parameters. This is just a side remark about the notation and how it appears. So, so far we have Euler and Lacroix, who reproduced his everything in the textbook. And here we meet Niels and Ricardo and his tautochrome problem. So this is another very interesting story. So the story is that he had two papers on that problem. One in 1823 and another one in 1826. Everybody knows the second one. Not so many people knew about the first one. And the first one is really remarkable. So what he did, he obtained the solution of the same problem using two different methods. The first paper is just beautiful. The other one is more a kind of an exercise on repeated integration. But the first one is wonderful, and it brings us also another message. So he was solving this equation that you see here. Sometimes many people say that Abel's equation was for the square root in the denominator. It is not true. He solved the general equation. And he obtains the solution in the following form here. And then he writes the solution using the symbol of differentiation with negative index. He didn't use those operations in his solution, but he wrote the result in this form. And this form says the whole story. He understood that actually he inverted the derivative of order alpha. And what he wrote here is the integral of order alpha. And instead of writing the integral sign, he wrote the derivative with negative index. This is the whole story. He had full understanding of this. And from today's perspective, what he was solving was just a fractional order differential equation in terms of so-called Caputo derivatives. And when you see such an equation, the inversion is obvious. This is how you eventually would come to this derivative of order minus alpha notation here. And so we wrote a paper about this, Niels Henrik Abel and the unnoticed birth of fractional calculus. And it surprised many people and even got to the list of the literature about Abel and his mathematics on the Abel Prize website. And for us, for me and my colleagues, Richard Megan from the University of Illinois in Chicago and my former student, Irina Tremorush, for us it is well, a kind of honor to see our names in the following list. I like the names here. Dirichlet, Galois, Hamilton, Mitterrand, Riemann, Weierstrass. Well, nice. I like this. So Abel, 23. But in the meantime, there was also Fourier working more or less in parallel. And there is another interesting point here. In his analytical theory of heat, 1822, after introducing his famous formula, he makes a remark that we can differentiate, and the order of differentiation can be any. It can be really any, and also including positive and negative. And it was not really noticed. Then we have Liouville appearing on the scene, and that was something unbelievable. He actually laid the foundation for everything what followed. And here I am showing you the cover of Jesper Lutzen's book about Liouville. And there is a special dedicated chapter on the theory of Liouville's contributions to the theory of differentiation of arbitrary order. I like also this. Arbitrary order is much better than fractional order. Somehow fractional is used for historical reasons, but the proper name should be arbitrary order, or arbitrary real order, or arbitrary complex order. So what did Liouville do? He started with Leibniz observation and came to this like differentiation of the function that allows expansion in a series of exponentials. Not so useful because there are not so many functions of this kind. He switched. And in a series of works, he really did wonderful, let me say, discoveries. He was the first to realize that when we stop using integer orders, the operator becomes non-local. So to evaluate the fractional order derivative, we need the whole interval to the left or to the right of the function, but not the vicinity of the point, like we do for integer order derivatives. And so he was the first to understand that there are left-sided and right-sided generalizations. That was a beautiful discovery. And here I'm using his notation to show this. At the bottom we see the left-sided fractional order integral. Above it there is the right-sided fractional order integral. Wonderful. He also came across something that is now called the Caputo derivative. the expression that is shown here is the Caputo half-order derivative of the function f. But this expression appeared during derivations and manipulations in Liouville's paper. And he also used the generalization from the viewpoint of finite differences. So he took the finite differences, okay, if we allow the order to be non-integer, then instead of finite number of addends, we have a series, infinite series. And this is what he already had. So we have here backwards and forward differences. And again, if we look at these expressions, we see that we cannot stop at the neighborhood of the point of our interest. We have to use a lot of values to the left for backward version or to the right for forward version. And those were really very, very important discoveries of Liouville. And he was also using those tools for solving applied problems. He provided examples of solution of real problems. Problem from Ampere's works, from I forgot the name. Okay, 3 examples he provided, and also he's used fractional order differential equations. He solved fractional order differential equations, and he solved integer order differential equations using fractional order operators. So he did a lot of what people did later. Then we have Philip Kelland, and in 1840 he provides an interesting information. Now we use those electronic sources. In the past, people were reading real papers. So he says, Leibniz suggested that generalized differentiation, and it was sleeping until Euler came to the playground. And then after Euler, there was some remark made by Laplace. And here he comes to the point. Fourier, in his opinion, was the first, and it is probably true, was the first who came with that idea of general differentiation for any orders. And not that for the particular functions, like let us differentiate the exponential or the power function, but for arbitrary functions. So that was an interesting opinion by Kelland. And he also tried to reconsider Abel's problem using fractional differentiation tools and manipulations. So this is the solution he provided. From today's viewpoint, we can have some objections, but basically, as I already mentioned, when people do something as the first, it is difficult to do everything correctly at once. And so the main idea and the main understanding was here. Then there was a series of works by British mathematicians, and it was William Center and other people who were playing with those differentiations of different functions with application of fractional derivatives to solving integer order differential equations and so forth. It was like, I would say, like experimental mathematics, like getting experience with those new tools, experience with their possibilities and their limitations. So this chapter of the development still needs some more exploration, because not all those sources are digitized. So I found some of them only here, scanned them, and I'm processing them now. Then we come to the next story, which is also a kind of a puzzle, I would say. It is Anton Karl Grünwald was working at German Technical University in Prague, and the picture you see here is the picture I obtained from that university, along with other materials shown nearby. And he wrote a paper on generalized differentiation using Liouville's idea, basically, of fractional order finite differences. And he published a paper in 1867. So how did he come to this paper? I tracked his biography, and yes, of course, he was visiting Paris and visiting lectures of Liouville. So very nice. In the meantime, in Moscow, there was another person, Alexei Letnikov, who also traveled to France and studied and listened to the lectures, visited the lectures of Liouville. I'm absolutely sure. So the idea is absolutely the same. And so Letnikov submitted a thesis. There is the story like to become a master in that Tsarist Russia. He used a trick. Go to Germany, get the doctoral degree there, come back and apply for the master exam. And this is what he did. And so when he submitted his thesis, the paper by Greenwald came to Moscow in the Journal of Applied Mathematics. And Letnikov decided to withdraw his thesis. But one of the founders of the Moscow Mathematical Society, Davidov, provided a letter of support claiming that Letnikov didn't know about Greenwald's results. And the Moscow Mathematical Society insisted in the defense. So he did defend his thesis, and he was active in the field for another 20 years. And Greenwald did nothing after that publication of 1867. So Letnikov published papers on the theory of differentiation of arbitrary order, 68, also about the historical development of the theory, of this theory. Also, he had some dispute with other mathematicians like Nikolai Sonin, and had to defend his results, so explanation of main statements of this theory and so forth. And then he was considering those integrals of fractional order that we have already seen in Liouville's works. He did wonderful work. And so still we have now the so-called Greenwald-Letnikov definition, which is a generalization of the definition of the differentiation using finite differences. This is okay. And this is, I think this is well justified. The other story is with the name of Riemann. Riemann was a student when he tried to do this generalization, and he did this in 1847 as follows from the manuscript. And he did not publish the manuscript because he had a problem. Like with the classical integration, we have the constant of integrations. In his attempt, he faced the arbitrary function of integration. He could not do anything with that. So he did not publish. This attempt was published in 1876 after his death, just for the completeness. And so this unsuccessful attempt was even remarked or commented by Arthur Cayley. Cayley is everywhere. When I was browsing those old journals, I saw a lot of Cayley's works in different fields of mathematics. And he also is present here. So what he says is exactly what I told you right now. Riemann tried, but he failed to work with that complementary function that appears in his attempt. By the way, Cayley's contribution you can find also in the Great St. Mary's Church in King's Parade. If you walk inside, you can find a column with this plate saying that Arthur Cayley and his wife contributed 2 windows to the church. So, okay, donated 2 windows. Another name, which is of great importance, is Hjalmar Holmgren, and it is practically unknown to many people. So, Swedish mathematician Hjalmar, when people see this HI, some might think those are 2 initials. No, this is just the start of his name, Hjalmar. And in 1865, he published the following paper on differential calculus with indices of any nature. And this is unbelievable. First, I like the notation here. I told you that notation is inspirational. And he uses here derivative, it is clear, the order mu, and the limits of integrations x and x0. So he has here x0 and x. And he uses the gamma, which became already the standard, and so forth. And the wonderful thing is that in his case, mu can be even complex, not necessarily real valued. Unbelievable. So this still needs to be explored more, because now people started looking into complex orders of differentiation. And I think I haven't seen any paper by modern authors referring to Holmgren's results. Okay, Letnikov also did the same work. So basically, you see, by the way, Holmgren also visited Paris. They all had a chance to see Liouville, to listen to his lectures, maybe even to talk, I don't know. But they all went through Paris. And so Letnikov also did. And he built a wonderful, complete theory for that. And what we have now, this version of fractional order differentiation is now called everywhere Riemann-Liouville definition. And as you could see, Riemann has nothing to do with that. Holmgren and Letnikov actually could be considered as somebody who shaped this approach. So Riemann is great. He did a lot of wonderful things, but not this one. So, as I mentioned already, Letnikov had some disputes with, here I see, and you can see here also, Sonin, and also with other, Pavel Nekrasov, and they had some disputes. And the reason was that Sonin tried to go this way, like starting with the Cauchy formula and generalizing this in the complex plane. But then it has a branch point, and things become more and more complicated. And for this version, I have not seen real applications. The only application of this approach is solution of some particular kinds of differential equations. And Katsuyuki Nishimoto from Japan even wrote, I think, 5 books on that, solving Fuchsian and other types of differential equations using this version of differential. He calls this Nishimoto's fractional derivative. But basically, if it should be called some name, it is Sonin. And I already mentioned that Liouville provided examples of applied problems solved using fractional order derivatives. And other people also did later. I like very much Heaviside, an engineer, open-minded engineer, going straight forward. I would say the way of thinking was very close to Euler. I will go straight forward, and then I will see what I get. And in his book, Electromagnetic Theory, in volume 2, he provides examples. Examples are always like this, where here you see half-order derivative. You see here derivative of order 1/2. Why? Because if you consider a semi-infinite domain, it doesn't matter, one-dimensional or two-dimensional, and then focus on the behavior of the solution on the boundary, then you arrive at half-order derivatives. So he was working on this, and this is his statement. There is a universe of mathematics between the complex differentiations and integrations. Fractional ones are just as real as the others. Sometimes he used the word integral, but integral in the sense of integer order derivatives. And this is like playing a fretless guitar. We are limited to those fixed frets, but those guitarists use a lot of tricks to get intermediate sounds. And this is the same idea. By the way, Leibniz wrote that music is a subconscious exercise in arithmetics. This is what he wrote. Maybe. This is a copy of some formula obtained by Heaviside, and you see here half-order derivative of 1 is equal to t to the power minus 1/2, and also divided by the square root of pi. Correct. Absolutely correct. So now I will return to that Liouville's idea of left and right, left-sided, right-sided, integrals and derivatives. And I like this statement by Theodor von Karman, famous engineer and mathematician, aerospace and astronautics, Hungarian origin, US career. And you see, he says, define great scientists as a man with great ideas, then perhaps Isaac is ahead of Einstein. He had 5 or 6 ideas. All other major scientists of our age are associated with just 1, or at most 2 great ideas. I like this. He's right. And he had a sense of humor. After this sentence, he wrote, I myself had 3, or maybe 3.5 great ideas. So, what was Newton's great idea? I think that the greatest idea of Newton was geometrization of time. Of course, before him, there was John Barrow and other people who worked on this, and we can also recall Descartes with his coordinates. But geometrization of time allowed Newton to use the tools of geometry to describe dynamical processes. And there is a trick. There is the trick. Here you see again that monochord that I showed under Leibniz picture. And here is some plot of a dynamic system with damping oscillations. And this plot is static. So we can think about those tangents and curvatures and everything. It is static. And what is missing? The causality. There is the past and there is the future. On a monochord, you can play left part of the string, right part of the string. But if you think about dynamical processes, you never have this future. we are sitting here and we don't know what will happen in half an hour. And so this is the point. And we look at standard textbooks and we see pictures like this explaining us that velocity can be approximated like this. What is interesting here? Efim Galperin, professor of automation and control and optimization, University of Quebec, he wrote also a paper. You can look in Science Direct for his full paper, but this is a letter to the notices of AMS. And he says, you cannot use the classical definition that we see in the books because it requires the values from the future. Don't forget, he works on automation and control. You don't have the future. You are going there, but you have the values from the past only. So, and basically his idea is that we should use left-sided derivatives in the applications. This is in the applications of mathematics and also in theory, we should switch to using left-sided derivatives. And he did not mention here any fractional orders. He was speaking about first order, you see here. So, left is right. Once a colleague from Cambridge was driving me somewhere here, and I said, oh, you are driving on wrong side of the road. He thought a little bit and then said, yes, I cannot say that I'm driving on the right side. So left-sided and right-sided derivatives. So what we have here is will, again, left-sided and right-sided. And don't forget that in the limit, when p becomes integer, they both give us the integer order derivative. So this is what we have here. Left-sided, right-sided. And at this point, we already have something interesting. We need good notation for this that takes into account. The trivial notation from the beginning was like derivative of order alpha. I don't care left or right. Or like this, just the classical notation. It should be clear from the context which version you use. Then Mkhitar Jibashan, Soviet mathematician, did also some theoretical work on differential equations, but he was using this notation, and here we already see left-sided and right-sided. This AB is the interval, and T minus A says that we are taking the values from A to T. B minus T says we are taking the values from T to B, and so forth. And Oldham and Spanier, the authors of the first, I would say, book on the subject, the fractional calculus, they were using this notation also, like Jibashan. By the way, nice example of collaboration. Keith Oldham was an electrochemist, and Jerome Spanier a mathematician. And so they collaborated on something that is called voltammetry. And because they were interested in the processes on the surface, the main mathematical tool was semi-differential equations. So differential equations with derivatives of orders multiples of 1/2. Okay, and Harold Davis, in his book and also in some papers, was using this notation, and I like this very much because here we have clear role of those terminals or limits, and the notation is unified. So this is what we have. For the first time, I found it in his work dated 1924. Now another step. Beginning of the 20th century, and people started working with materials, and it became very clear that there are no fluids, ideal fluids, there are no ideal solids, everything is in between. So in the case of ideal fluids, the stress is proportional to velocity, which is first order derivative. For ideal solids, the stress, mechanical stress, is proportional to the deformation, zeros derivative. So the trivial idea was, in between, let's take the order between 0 and 1. And there were many people contributing to this, but I think the most important is George William Scott Blair, a British engineer, mathematician, physicist, rheologist, one of the founders of the British Society for Rheology. And he did a lot of experimental work describing dairy products. How can you say, how can you describe the hardness of cheese, the softness of cheese, and so forth? So that was his main idea, and so he was working on that. And in one of his books, Measurements of Mind and Matter, he stated that integer order derivatives with respect to time, such as velocity and acceleration, depend on the classical definition of the equality of time units. And this is Newton with his equably flowing time, with his ideal mathematical equably flowing time. Okay, so he was perhaps a very deep thinker. And he always used those tools in his models. You see here elementary rheology. This is a new picture principle of intermediacy between those fluids and solids and so forth, a series of books that I have by Scott Blair and so forth. And in the University of Aberystwyth, on the other coast, there is his collection of, Scott Blair collection of his publications and the publications by other people he collected. I've been there to work and process that. So something like quasi-properties and so forth. He even reinvented the fractional differentiation. He didn't know that it existed. He reinvented, he was disappointed to see that it is already known. And you see here, he even introduces his notation. F stands for fractional differentiation. Maybe naive, but I like this very much. And so a big change came with the contribution by a physicist, tectonophysicist basically, Professor Michele Caputo from Università La Sapienza in Rome. And in his paper in 1967, he comes with this version of the definition. And if I compare this with the Riemann-Liouville so-called definition, I see that the order of differentiation and integration are swapped. Here, he first differentiates and then integrates. Okay, the reason is that in this form, it is possible to use the classical initial conditions in differential equations. That was the real meaning of his discovery. The picture is here from 2012 in Ravello when he was speaking about his research and wrote his definition. And he also proceeded like Euler did, like Heaviside did. He proceeded immediately to solution of real problems. And in this book, Elasticità e Dissipazione, it is 1969, he provides a lot of problems for viscoelastic materials with solutions. And 3D versions of this is available in his lectures on seismology and rheological tectonics, 1992. So that was a very, very important step forward. I will return to those things a little bit later. Another great statement is from Svante Westerlund. He was, for several decades, a chief engineer at a factory making capacitors. And capacitors didn't correspond to the theory. And the conclusion was, why? Because the model is wrong. And he suggested fractional order capacitor theory, and it is accepted and it is now praised. So, and his statement was also that that matter has memory. This is a very deep statement because we have omnipresent dissipation. And dissipation, energy losses, is the subject that we omit if we use only integer order derivatives without extra terms that complicate the models. So, some other approaches, generalized functions. Using this standard function, power law for positive t and 0 for negative t, we can write the Riemann-Liouville and the Caputo derivative as convolutions. Riemann-Liouville is the derivative of the convolution of the function in this phi. Caputo derivative is the convolution of the derivative of the function f and that function phi. So this is what we have. If we go further, we can conclude that they are related. So this is the Riemann-Liouville, this is the Caputo derivative, and these are extra terms. And these are extra terms. And we can, if we compare this with the known relationship from the theory of distributions or generalized functions, we can conclude that the Riemann-Liouville definition is actually a generalization of the notion in the sense of distributions, the notion of differentiation, while Caputo is generalization in the sense of the classical function. And this is also a very interesting situation. So historically, Riemann-Liouville came first. Riemann-Liouville version, I should put quotes on this all the time. It appeared as the first, but from today's viewpoint, it is basically something that works only for distributions. And Caputo is in the classical sense. And with Professor Nicole Heymans, we wrote in 2006 a paper explaining how to interpret initial conditions for fractional order differential equations with Riemann-Liouville derivatives. And we proved that the only physically realizable initial conditions for such equations are impulses. That's all. And Caputo allows those classical initial conditions like initial position, initial velocity, acceleration, and so forth. There is also another variation like sequential fractional derivatives. So how do we get those derivatives of order 1, 2, 3? By sequential differentiate. And this is what we do. If you replace each first order derivative with some derivative of order alpha, then we get what was introduced by Kenneth Miller and Bertram Ross. And they wrote a book on that. And this book deals only with differential equations of rational orders. And of this kind, basically. So, again, here I found something that probably nobody noticed before. A paper by Mikhail Vashenko-Zakharchenko, Ukrainian, 1861, from Kiev. And in a paper on fractional differentiation, he comes with a remark that we can have 3 derivatives of order 1/3, and this is still derivative of order 1. So basically, this is a very interesting point, sequential derivatives, and it can be also generalized like the previous ones. Riemann-Liouville derivatives can be, and Caputo derivatives can be considered as a particular case of sequential derivatives in a different sequence. So the cumulative order is the same, but the properties are different. By the way, we face those sequential derivatives when I start with some basic physical law and apply other, like for example, continuity or moment preservation or energy preservation. I do differentiation of the differentiation. For integer orders, we don't care because everything is working perfectly there. But if we start working with fractional order models, it is not so easy. And the next levels are variable orders and distributed order derivatives. Some properties that I would like to preserve are violated there. But there are still a kind of non-integer order differentiations, and they still make sense because, for example, what is the change in order? The change in order, like the muscle, I go to do some exercise and I have to warm up. And my muscle has different properties before warm up and after. This, or you play some instrument and it detunes because of those tensions. Okay, what to do? I already mentioned capacitors, and we use those laptops, and each laptop has that power supply. Yep. And sometimes it stops working because those power supplies are using switched capacitors, and they dry out and they stop working. So the orders change, and the result is the system stops. So the first analog device exhibiting fractional order behavior was designed by Gary Bohanna from the University of Montana. And when we played with that, it was interesting. It was a fractional order element, analog fractional order element, but with time, it obviously became more and more like a capacitor. It started from order 0.45 and became more like order 1. And so it was recorded and processed, and then we found that it is a general property. We did also measurements for typical electrical circuits like ladders and nested ladders. Not going into detail how we do this. At each time instant, we just estimate the current order, then we let the system work further and estimate the order of the system, identify the order of the system at that moment, and so forth. So the order was changing. Fortunately, there was already a tool for this suggested by Stefan Samko and Bertram Ross in 1993. And those are integrals and derivatives of variable fractional order. Variable order, I would say. This is what really works. Some people provide the whole zoo of formulas because it is easy to write formulas. It is not so easy to produce formulas that are related to real world. So here we also have left-sided and right-sided versions. And of course, if you have left and right-sided, you can combine them and produce symmetric version. Okay. So I skip this. I and my colleagues, we have a lot of software. Software is available in MATLAB, MATLAB Central File Exchange. You can go there and download and play if you want. And the historical remark is here, like Professor Caputo also is the one who introduced distributed order fractional derivatives. So, well, distributed order fractional derivatives in his book, Elasticity e Dissipazione. Now I'm coming back to that letter that Leibniz wrote to L'Hopital, the same letter. And in that letter, he raised the following question. I like this second edition of his correspondence because something appeared here. It was not in the first edition of the 19th century. In the 21st century, it was added based on the manuscript. And so this sum is derivative of negative order. So this is what he writes here. And he continues, the sum is a differential with negative exponent, and we can ask what is a differential whose exponent is a fractional number. We can express it in infinite series, basically we can use formulas, but what does it mean in geometry? And of course, we have those trivial geometric interpretations of derivatives and integrals. And so I provided some answer, but it was based on the interpretation of Stieltjes integral. And that itself was interesting. Stieltjes introduced it in 1894, but the geometric interpretation came almost a century later by Balak. And I used this Balak's idea to provide geometric interpretation for fractional order operators, which I called shadows on the walls, you will see in a moment. And here is just a remark for fun. Leibniz asked his question in 1695. I provided my solution in 2000. 305. I think it is the second long-standing question after Fermat's last theorem. Andrew Wiles, you saw that green board in the Newton Institute. It was on the 20th anniversary of the presentation of the proof. And it took 358 years. What's the difference? Nobody knew about Leibniz's question. So, nobody. Everybody knew about Fermat's last theorem. But still a funny remark. And here is the demonstration. What do I mean? So this is the fractional order integral. The function that I am using here, function g, has self-similar shape. And basically what I do, I build this green fence, and it throws two shadows. The red one is the classical integral of order 1, integral of the function f, and that's all. The blue one, that is also changing its shape, is the fractional order integral at each particular moment. You can find my work easily if you search for my name and go to Google Scholar and find the paper. And in 2013, we provided also an interpretation for distributed order operators. And I like this. We all have mobile phones. Mobile phones, electrical cars, and everything use cells, power cells, to provide everything. And basically, this is a set of those elements. And each particular cell has different response. What we have here. And the response of the battery is an aggregated response. Or you can think about the aggregated response of the group of people or population of a country in general, and so forth. And so I'm finishing. I'm absolutely at the end. And so back to the same letter. I like those works like Euler's paper and like this letter by Leibniz. And he writes to L'Hopital. This is the end of the letter. After he presented his views, and you are one of those who can go to the furthest in discoveries. Great, Leibniz is writing this to L'Hopital. And I will soon be obliged to pass my lamp to other people. Yeah? I would like to have much to communicate for this verse. And this, what is written there, this spiritum nihil est, what we know is nothing until we share it with others. And so is the truest in that thoughts which were little in themselves can give occasion to much more beautiful ones. This is like from a small idea, from some short discussion, a beautiful discovery can be developed or can bloom at some point. And there are two posters also available on the net, History of Fractional Calculus and Modern History. Both are created by late Professor Tenreiro Machado from Portugal and Professor Virginia Kyriakova from Bulgaria and Professor Francesco Mainardi, a student of Professor Caputo, by the way. And they compiled such nice posters. And you could see how it is rapidly developing, even in terms of those monographs that you see here. So thank you very much for your interest, for your patience, and I am happy that you stayed here until the end. Basically, mathematics is a tool. This is what I think. Mathematics is a tool. And now we are in the period where those models might be very useful for modeling rubbers, polymers, complex structure, and so forth. And this is what we work on, not only for modeling, but also for controlling dynamical processes. And here are some books. The first one here is the proceedings of the conference organized by Bertram Ross, who was a PhD student at that time. Wonderful collection of works. The second one is volume 111 from Mathematics and Science and Engineering, Oldham and Spanier. The next one is derivatives and integrals of fractional order and some of the applications. Okay, not real applications. Those are applications to theoretical problems, basically. Some Kilbas and Marichev, translated later to English and recently to Chinese. Miller and Ross, I already showed you. This is my book, Fractional Differential Equation, in the same series, Mathematics and Science and Engineering, but volume 198. Okay, and these are very rare pictures of Keith Oldham and Gerald Spanier that we got for some of the articles that we were writing in the past. So this is the end of my talk. Thank you.